I trust you did well on that quiz you just took, and that's the kind of math you'll see largely on your test, on your exam, on Wednesday, coming up in lesson 42. We've already beat the chapters 3 through 5 math pretty hard, okay, between the chapter 3-4 test and the chapter 3-4-5 test. So that math will not appear. Terms will appear from chapters 1 through 5, but the math will be entirely from chapter 6, which is what you just did, and chapter 7, which we're going to cover today, just a little bit of the math. Now, in chapter 7, it's all about vectors. And again, what is a vector, Audrey?
It has magnitude and direction.
Good. Any quantity that has both magnitude and direction. And we said that when we draw vectors, we'll draw them how, Michael? With an arrow, where the length of the arrow indicates the relative magnitude and the arrowhead location tells you the direction. We said that if two vectors have the same magnitude and direction, we would describe those vectors, Kendall, as being same magnitude and direction. Equal. They're exactly the same, so they're equal vectors. Now, she used the term parallel vectors. Parallel vectors are vectors which have the same direction, right? Which makes sense, right? If they're parallel, they're going in the same direction. What if they're going in the opposite direction? How would we describe those, Michael?
Negative.
Well, I mean, that's true. One of them would be negative, the other positive. Kendall? Anti-parallel. So parallel, same direction, anti-parallel, opposite directions. If vectors act literally along the same line with each other, I don't know if you've ever gotten into some sort of like a shoving match with siblings. Surely not. Y'all are way too mature for that. Or maybe, you know, for instance, football. I love football, right? Running backs carrying the ball, and like the two guys come together to try to tackle him, and one of his guys comes behind to try to push him. Well, they're all acting right along the same line. A couple guys acting this way, and a couple guys acting that way. They're all acting along the same line. How would we describe vectors that act along the same line, anyone? Collinear vectors. What about vectors that act at right angles? For instance, the running back's trying to run down the field this way, and a guy races over from across the field and tackles him from the side. Okay, so we've got a vector going this way, we've got a vector going that way. If they're at perfect right angles to each other, Michael? Perpendicular vectors. And what if the vectors, they're not collinear, parallel, or anti-parallel, they're not perpendicular, just not any of those things. It's just kind of weird angles that they would form. Skewed vectors, and that's where we left off. A couple more terms for you to get in your notes. With all of these vectors, we kind of have this idea of them all acting at the same time on the same object. We would refer to them then as being concurrent vectors. Concurrent vectors. Two or more vectors that act on the same object at the same time. Two or more vectors that act on the same object at the same time. Two or more vectors which act on the same object at the same time. We'll refer to those as concurrent vectors. And of course, concurrent vectors can be collinear. They can be parallel or anti-parallel or perpendicular, right? Skewed. They could be all of those things. But we use the term concurrent to refer to the fact that at the same time, they're all happening on the same object. Now, again, if we had, for instance, running back going this way, let's suppose we had a tackler who approaches him at an angle and tackles him. Let's suppose there's another tackler who approaches from behind to tackle him. And they all three converge at the same point at the same time. They all have their own velocities at impact, okay? We'd have three concurrent vectors then. Well, the question is, what happens to the running back, right? Probably he kind of goes like that, okay? Because you got two forces coming from, or two impacts from the side, and there's more impact going forward than backwards. So he probably still goes a little bit forward upon being tackled. Obviously, that doesn't account for the mass of the other players, right? But probably something like that. This would be the outcome of the other vectors, right? We have a name for the outcome. It's called the resultant vector. The resultant vector. The resultant is a single vector that shows the outcome of multiple concurrent vectors. A single vector that shows the outcome of multiple concurrent vectors. And that's what chapter 7, which again, we're only going to touch on a little bit of it here today. We'll be reviewing tomorrow exam. And after the exam, we're going to do a lot more with finding resultants of all different styles of vectors to where you'll be able to take any scenario and find the outcome of it. We're going to start with just a couple really basic ones, but this is really the gist of all of it is, okay, all these things happen at once. What's the resultant? What's the outcome? What actually ended up happening because of this? Okay, so multiple vectors that act at the same time, class, are called concurrent vectors, and the one vector that shows the outcome is called the resultant. I'll usually represent the resultant with the letter capital R. Just in this class, that's not an official shorthand or anything, but it'll make life a lot easier for you. A single capital R, as I'm writing it, I'm using that to refer to the resultant. So the next thing you note is finding the resultant of collinear vectors. Finding the resultant of collinear vectors. And it's really pretty easy. If they are parallel, which remember means same direction. If they are parallel, add and keep the direction. If they're parallel, if they're acting in the same direction, add and keep the direction. For instance, if Michael is running down the football field at, say, 7 meters per second, and suppose Thaddeus comes racing up behind him, that's pretty fast. Suppose Thad comes racing up behind him at 9 meters per second and just crashes into him. Now, Michael will probably lose his balance and fall, right? And Thad gets a red card. Well, it's a football game, not soccer, not football. Anyway, but for a brief moment, what would be the outcome of these two vectors? Well, it should be pretty straightforward. 16 meters per second is the resultant, the outcome of that. And if Michael happens to be running east, as Thad ran up behind him, also going east, and we'd keep east. If we didn't have an actual direction, we would just assume positive showed the direction, right? But suppose Michael was running down the field. Now again, this doesn't account for mass or any of those things, but we're not looking at the causes of the motion. We're just looking at the motion itself. Assuming if there were equal mass, and there isn't, but if you were running at 7 meters per second, and supposing you had Thad running at 9 meters per second the other direction, and there were this collision of equal masses, what would end up happening? Who would win, class? If they had equal masses, the guy going faster would win. So what would happen with Michael? He's running down at 7, and all of a sudden, boom, hits a brick wall called Thaddeus, and he goes, not just, well, down, yes, but before that, for a split second, before he goes down, backward at 2 meters per second. We could also show it this way. We could show from here to here 9 meters per second. And you can see the gap right here is our resultant of 2 meters per second. But since it's in the opposite direction Michael intends, we'd say negative. Or if we said Michael was running east and Thaddeus was going west, we'd say 2 meters per second west. Because rule number 2, if anti-parallel, subtract and keep the direction of the greater. Subtract and keep the direction of the greater. Does this sound vaguely familiar? Like you've heard this before? Add and keep the sign, subtract, keep the sign of the greater absolute. It's basically working with signed numbers, isn't it? Same thing we did in algebra class. In fact, we actually used vectors, I think, when you were in 9th grade. Michael would remember this. But when you were in 9th grade, I think I used vectors to teach signed numbers. I said if we had a little birdie, and the little birdie was flying merrily along at 5 miles per hour, and a wind blew up behind the birdie at 3 miles per hour. Now how fast does the birdie go? 8 miles per hour. And since they're both going in the same direction, we say they're both positive, so positive 8, add and keep the sign. If the birdie were flying this way, well, we'll say that's negative 5 because it's the opposite direction. Suppose the wind was also going this direction, negative. Okay, now what's the answer? Negative 8, because you add and keep the sign. If they're going in the same direction, you just add them together, keep the direction. But let's suppose Let's suppose little birdie is flying along merrily at 5 miles per hour, and the 3 mile per hour breeze was in birdie's face. Now, how fast does birdie fly? If it doesn't adjust, obviously. 2 miles per hour, but still positively, right? Because the positive beats out the negative, right? And I think we also had the one where the bird was flying and the hurricane blew it back into a tree. You remember that one? Sad day for the birdie. Anyway, pretty straightforward, right? So look in your textbooks, if you would, at page 96. Page 96. And look at example 7.1. We've got these two vectors, one going south at 7, the other going south at 12. Or you could think of them as going negative if you wanted to think of south as a negative direction. We live in the south, we prefer not to think of it that way. But there are those, up north snobs who might feel that way. So what would you get if you added a -7 and a -12 class? -19. Or if you went 7 south and 12 south, that's 19 south. Really easy, right? All right, look at the next page, example 7.2. We've got now a vector going 7 units north and a vector going 12 units south, or -12 and +7. What's the outcome? -5 or 5 south. South was stronger, south wins. It's not how the Civil War went, or the war between the states, or the war of northern aggression, whatever you call it. But that's how it works here. South wins. South was greater. Questions on that? Pretty straightforward. Okay, you see the little example there at the boat. If the boat is going upstream at 8 meters per second, and the current of the river is flowing, obviously downstream at 3 meters per second, what is the resultant velocity of boat A? 5 meters per second upstream, right? Boat B is going downstream at 8 meters per second. The current is going 3 meters per second downstream. What's the resultant velocity? The boat was already going 8, and the current's going 3 downstream. 11 meters per second downstream. Pretty easy. Turn the page. Example 7.3. So this is not scary math, right? This is easy math. Good. Example 7.3. Read it for us, Kendall.
A bird flying east at 25 meters per second encounters a headwind of 5 meters per second. What is the bird's resultant?
All right, now, you'll see these terms, okay? Headwind and tailwind. Headwind is wind at your head. And birdie doesn't fly this way. Birdie's like that way, right? Head forward, tail backward. If the wind hits its head, is it working with the bird or against the bird? Against. Tailwind is wind that hits tail. All right? Would that be going for or against bird? Same with airplane as well. The nose of the airplane, we don't call it the head, we still call it a headwind. And tail of the airplane, we do actually call it the tail, right? It comes up from the back, okay? So, bird flying east, headwind of 5 meters per second. So are they going in the same direction or opposite directions? So add or subtract. Who wins, bird or headwind? Bird. So we subtract to get 20 meters per second, and it's still going east because it won. But let's suppose bird flying east encountered headwind of 35 meters per second. What would be the resultant velocity, assuming the bird did not compensate? Which that's a very fast bird, by the way.
Squashed bird.
Well, squashed bird potentially, but what's the resultant velocity? -10, or we would say 10 meters per second west, because bird is now flying backwards through no fault of his own. He just happened to get into a tropical storm right there. All right, questions? Not trying to insult your intelligence or anything. Turn over to page 109. You're about to be insulted. Do numbers 1 and 2, problems 1 and 2 on page 109. Problems 1 and 2 on page 109. Number 1, a vector of 15 units acts to the left, a vector of 3 units acts to the right. What is their resultant? Audrey? You're correct, it's 12, but we need a direction. Remember, it's a vector, so 12 units. Which direction wins? Well, it used the terms left and right, so we'll stick with those. Left. 12 units left. How many had that? Okay, look at number 2, excuse me. A vector of 13.2 units acts upward, a vector of 22.6 units acts downward. What is the resultant, Michael?
9.6 down.
Ooh.
Down.
Kendall?
Negative 9.4 down.
Either negative 9.4 or 9.4 units downward. Just careful on the subtraction. 9.4 units downward. Pretty easy. Okay. Let's move on to something a little bit more challenging. All right. Next thing in your notes. Finding the resultant of perpendicular vectors. Finding the resultant of perpendicular vectors. Now, for those in pre-calculus, this is also stupid easy. For those who are not taking pre-calculus or have not had pre-calculus, this will be a little bit of review from the past. So, Kendall, I'm going to direct my attention primarily to you. But all of you go and get these notes down. First things first, you'll want to arrange the vectors head to tail. Meaning the head of the primary vector will touch the tail of the secondary vector. The head of the primary will touch the tail of the secondary. Then draw the resultant from start to finish. The drawing is going to be very important for perpendicular vectors. For instance, look back, if you would, at, actually don't look back, let me just give you a problem. Let's suppose we have this is the Chattahoochee River, and the Chattahoochee River, as you should know, flows south. Let's suppose it's flowing south, the dams are not open, and you're in a portion where it's a little bit milder. Let's go with the 3 meters per second that we had in the problem earlier with the 2 boats. Let's suppose a boat is trying to go across the river east at 5 meters per second. Okay, so a boat is going east across the river at 5 meters per second, and the current is going south at 3 meters per second. Which of these would we consider primary? Well, primary would be the intended action. The intended action is the guy in the boat wants to go across the river east. So my primary vector I would draw first. And then at the head of the primary, I will start with the tail of the secondary, 3 meters per second. So we have a 5 meter per second east and a 3 meter per second south. And the resultant will be drawn, I'll usually draw it as a dotted line, from the start to the finish. This shows graphically in picture form what will actually happen to the boat. The boat will not go east, it will go that way, kind of southeast. Does that make sense? It'll be pushed off course, assuming no compensation, right? Now, naturally, you would actually end up compensating and constantly recorrecting and recorrecting, but if you didn't, let's suppose you were blindfolded for some reason going across the Chattahoochee, and you're just kayaking, merrily thinking you're going east. Somebody started you off in the right direction, you just keep paddling east, and you just keep getting pushed off course, okay? So no course corrections allowed. Here is the resultant. Well, if you think back to your geometry days, Kendall, if I have 2 sides of a right triangle, 2 legs, how would I find the hypotenuse or the resultant? Yeah, the Pythagorean theorem, so back from our geometry days. So we would say that the resultant squared, which will be the hypotenuse, equals one of the vectors squared plus the other vector squared. And of course, you could do this on your calculator, the 5 squared plus the 3 squared, and you'll take the square root to get just the resultant. All of you doing it, but Kendall's going to give us our answer. We're going to get an answer of
5.83.
blah, blah, blah. Now, we only have 1 sig fig to work with here, so technically we'll round it off and say, Kendall, 6 meters per second. Oh, this was south. 6 meters per second. So, if you would, number 1, to find magnitude, Pythagorean theorem. And bringing back flashbacks from a couple years ago, right? Pythagorean theorem, not hard. The two legs will always be the two vectors, so you just use the Pythagorean theorem to find the hypotenuse. Square them, add them, take the square root. For the other thing, I'm going to have to take you all the way back to your junior high days. When you were in junior high, you talked about something called trigonometry. And there was an old Indian saying, Sokatoa. Do you vaguely remember hearing Sokatoa? Sine, cosine, tangent, you vaguely remember those? Well, there's only one that you need for now, and it's called the tangent. In any right triangle, the tangent of any angle is equal to the length of the opposite leg divided by the length of the adjacent leg. We would say the tangent of, and we'll use this, it looks like an O with a line through it. It's the Greek letter theta. It's used to indicate an angle. And this right here is my angle. This is where the boat was supposed to go. This is where the boat did go. The angle shows us what direction off course the boat was pushed. Does that make sense? By this current. So the tangent of theta equals opposite over adjacent, where the secondary vector will always be the opposite and the primary vector will always be the adjacent. So on your calculator across the top row, you see sin, cos, tan. You're focused on the tan. However, we know that the tangent of this angle theta is 3 opposite over 5 adjacent. We don't need to know the tangent. I already know the tangent. What I want to know is the angle. And so what I need to be able to do is to get rid of the tangent from this side. The way you'll do it is by using the second function of the tangent, but you'll have to do it to both sides. So that theta is going to be the arc tangent, we call it. It's the second function on your calculator of 3 over 5. So what you'll do on your calculator is do 3 divided by 5 or 3 fraction 5, either way. You'll hit the second function, tangent, because number 2, for direction or angle, you're going to use the arc tangent. So Pythagorean theorem is used to get the magnitude, and the direction is found using the arc tangent. So we'll do 3 divided by 5, take the arc tangent. What is the angle theta here? Kendall?
30.963.
Good. We'll round it off now. We technically only have one sig fig. Let's say it was 5.0 and 3.0 because I hate the one sig fig. Let's say this is 5.8 then. Then we would have 31 degrees. Now notice how we'll describe this. The boat was pushed 31 degrees and it was pushed to the south of east. It was trying to go east and it got pushed to the south, didn't it? So we'd say at 31 degrees south of east. There's the direction. There's the magnitude of our vector. Pythagorean theorem for the magnitude, arctangent for the direction. Let's suppose, though, that there was a storm brewing and the wind was coming, listen, from the north. Now, if wind is coming from the north, which direction is it going? South. From the north means it's going south. Suppose we have a 2 meter per second wind from the north. Well, now there's 2 secondary vectors, aren't there? But they're collinear. They're parallel. So collectively, class, what is our secondary vector now? Collectively, we now have 5 meters per second between wind and current going south. Well, now we go to find the resultant. Again, we'll use the Pythagorean theorem. So at your seats, use the Pythagorean theorem. Primary vector is still 5. Secondary vector is now 5. And what will we get for our resultant? How fast is the boat going now?
7.1.
All right, everyone got that? 7.1 meters per second. All right, or 5.0. Okay, 7.1 meters per second. Notice it sped up a little. Now, it also got pushed further off course, though, didn't it? Because we know that the tangent of this angle is what over what, class? Opposite over adjacent. So the opposite is 5. The adjacent is 5. But we'll take the arc tangent. Well, what is 5 over 5, class? 1. So we'll take the arc tangent of 1. And Kendall, what do we get for our angle theta?
45.
Comes out evenly, doesn't it? Right, you might, by the way, remember a 45, 45, 90. Stay with me. If the 2 legs are equal, we have a 45 degree angle here. So we'll say it was pushed 45 degrees. It was trying to go where? Where's the boat trying to go? East. But he got pushed to the south of east. And this is how we would describe it. Let's look at one example problem very quickly, and then we will be dismissed. Page 99. Page 99. Look at the example problem. Again, they're kind of dumb with the way they set it up, but whatever. We got two vectors, A and B. One goes 250 units to the right, and one goes 175 units upward. All right, so they have the primary vector, 250, and then secondary, 175. Do you see how they formed a right angle with the resultant? Well, to find the magnitude of the resultant, you see that they squared the 250, squared the 175, and took the square root. Pythagorean theorem. They found the magnitude to be about 305 units. Then they had to find the angle. Well, the opposite is 175. Divide that by the adjacent 250. That's 0.7. And they took the arc tangent of the 0.7. That gave them an angle of about 35.0 degrees. So we would say that the resultant is, and here's how I would say it, 305 units, because they didn't say what the units were, at 35.0 degrees above right. It was trying to go right, and it was pushed upward, so upward from right or above right. Make sense? Did not get as far as I wanted to today, but I do have a homework handout for you that will give you some practice with both collinear and perpendicular vectors. As always, if you're watching on YouTube, the handout is found in the description of the video. For you in my class, here you go. And this will wrap up the math for the exam. We'll spend a lot of time on this tomorrow. We'll quickly review over terms. I would strongly encourage you, be reviewing terms tonight. The exam is not until Wednesday, but start this evening looking over chapters 1 through 6. Chapters 1 through 7, really, because we did give you some terms here. Look over those terms. We'll review those tomorrow as well. All right, you are dismissed. Have a wonderful rest of your day.